Hi, this is the video for section 1.1. Last time we talked about what Calculus 3 is, and so let's begin. So before I start, I want to talk about a little bit of notation. So when I use this symbol R with the double lines, that means the real line. R2, the 2 is indicating my dimension, that is how many variables I'm going to think about at that time. And that'll be things like x comma y, things in your coordinate plane. Space, the 3 is also indicating my dimension, and that's 3 things I'm considering, x, y, and z. So 3 things under consideration at once. And in general, R with an n is talking about n variables, which means I'm just thinking about n directions or n items being considered simultaneously. Mathematicians, of course, will let n be infinity, and they're fine with this, but we don't need to go that far. If n is infinity, you can kind of think of it as a sequence, but there's also an idea of infinite dimensional space, but this gets into the direction of topology, which is a little bit beyond this course. The only other thing I want to remind you of is this notation. When I have these brackets, I mean that A and B are in this set, and this is indicating the set of all numbers beginning with A and ending with B and in between line segments. The parenthesis means I'm not including the A, and the closed bracket means I am including the B, and so as usual. I've seen other notations where if they mean what I'm using the parenthesis for, they'll use a bracket in the direction it shouldn't be to mean this, and I've seen other notations, and I just want to make sure we're on the same page. So, what does the question plot y equals 2x mean to you? If someone walked up to you on the street and for some reason thought it appropriate to ask you to plot y equals 2x, what would you do? Well, you either would pull out a phone and you would type it in and make it appear somehow, or you would make like a table of values and calculate it and show them, or you'll just remember that this is a line that has slope 2 that goes through the point 0, 0, and you will draw it from definition essentially. But no matter how you do it, that's an appropriate response, and it's the one that you've been trained to give over your mathematical career probably. But this is also an appropriate take on that picture. If I'm plotting y equals 2x, then you should think of the equality y equals 2x as a restriction. Because what's really happening here when I plot this? Well, I'm essentially plotting and shading ordered pairs x comma y that have the property that when I plug that ordered pair x comma y into this equality, I get true out somehow. And if I plug in an ordered pair x, y that in this picture is not shaded, it'll end up being false when I plug it in. So like this point here at 1, 0. This point was not shaded on this line. And the reason it wasn't was because if you took x equals 1 and you plugged it into this, you would get 2. But if you took y equals 0 and plugged it into this, you would get 0. And the statement, because an equality is a sentence, it has a noun, it has a verb, and it even has an object. Although you could read it both ways. This is maybe not the... anyway, it's a sentence, and it's either true or false. And so when you plug this point in, you get false, and so you don't shade it when you draw this picture. Now, this equality is not saying anything about z. If z was 7, this equation is still true. If z is 8, this equation is true. If z is negative the square root of 18, which is 3 root 2, it would still be true, because it doesn't care what z does. So if you're in a place where it's appropriate to talk about 3 dimensions, if you're considering 3 things at once, then that's certainly an appropriate picture. This line down here is what you usually think of as a line y equals 2x. and then just the z direction, since there's no restriction on z, drags it up and in fact downwards in both directions. I just didn't draw the downwards because it doesn't look good. So I like to say that z is free. That is, it's free to take any value at once because the equation is not restricting it. Okay, all this being said, let's talk about functions. Now, throughout calculus, you're told, or questions are given to you that start with let f of x equal x squared, find the equation of the tangent line. In fact, I did it to you earlier in the previous lecture. And that's sort of an ill-formed question. In reality, a function requires 4 pieces of information, or it's not formally a function. You need a name for the function. So, f, we call them, or sine, or logarithm, or exponential. And that's just so that when we write things down, we can distinguish them. That's, maybe to a computer scientist an obvious thing, but to someone else maybe not. In computer science, if you try to, in programming in general, if you try to give the same name to 2 different things, the computer will just say no. And so, in the way we think of these things, that's important. A domain. Now, domain means inputs, so it's x-axis stuff. Stuff we're going to plug into this function. A codomain. Now, codomain is where the range lives, but it's not necessarily the range. And I have some examples that will make that very clear. And finally, you need a rule of assignment. And normally numbers 1 and 4 are the things that you're given, because you're always told f of x equals x squared, but you're never told necessarily the domain each and every time this happens. Generally, it's assumed that domain is the largest possible domain you could have. So when I write a function, I always write the name of the function, put a colon, and then I put the domain, which I call x, and the codomain, which I'm calling y right here, and I give a rule of assignment. Now, at some point, I'll probably be lazy about this, but I want to really emphasize these 4 things, because understanding what functions are helps you distinguish the different kinds of things that are going on in Calc 3. And if you really understand how these sorts of functions are different than these other sorts of functions, then you see the point of what we're doing, at least in terms of the theory. So when we graph a function, what do we do? Well, in Calc 1, you're usually given a function whose variable is a real number, whose independent variable is a real number, and whose codomain is the real line. And this is common. So you end up with pictures like this, where you have your domain on the x-axis, and you have your codomain on the y-axis, and in this case the range is equal to the codomain. They're the same thing, because the range is where the outputs live, and it's these y values. And that's fine. So let me go through a few examples of functions, just to make sure we're all clear on the definitions. The domain's a set of inputs, the codomain's is where the outputs live, and the rule of assignment. So, okay, here's x squared, our friend, and in this function I'm declaring that the domain is the real line and the codomain is also the real line. So I have the entire x-axis as my domain and the entire y-axis as my codomain. And this is the standard picture. This is what you normally would draw, and I'm going to be very careful about arrows in these pictures. So because the domain is the real line, then the arrows go forever in both directions, and same with the codomain. Now compare this function to this function. Now I still have a name, I still have a domain, I still have a codomain, and I still have a rule of assignment. I have a similar looking picture, but because my domain is stated as -2 to 2, then my only focus is there. And so when I draw this function, I will draw it differently than I drew the previous, because the domain is different. It is a different function. It has a different domain. So one of the 4 things is different. And so I put these filled in circles to indicate that this is a closed edge and a closed edge. And I did the same down here. I forgot to label the edges, but that's okay. So compare this to this function. Now, in these 2 cases, the domains are the same. But what I've changed on this one from the previous is I've changed the codomain. So this codomain starts at 0 and it goes to 4. It does not go below the x-axis. And in this case, finally, we've arrived at a place where the codomain is the same as the range. And those who've had, say, linear algebra might have heard of this called an onto function, where the codomain equals the range. And onto functions are very nice for lots of reasons. But in my opinion, the domain restriction is more important, but in the overall picture, understanding domains and codomains as inputs and outputs is all I'm really trying to focus on here. So one more example. Here I've chosen the set of my inputs to be 0 to infinity, and my outputs are also 0 to infinity. Now, this one versus this one, I prefer this one, because I can take an inverse function of it if I wanted to. The inverse would be square root x. Now this function would have two inverses, plus and minus square root of x. And that minus comes from this extra left piece appearing here that it doesn't appear here. What's different is that this function is not what we call one-to-one. And one-to-oneness is also very important. You've come across it in, say, trigonometry, when you're trying to define inverse sine. Either you were just told that inverse sine takes these numbers as inputs and gives these numbers as outputs, or you had somebody that explained why this needed to be done. And the reason why is because if you need the inverse to be a function whose codomain is the real line, you need to restrict your domain so that you end up with a situation like you do not have here, where two different inputs have the same output. You don't want that if you want an inverse. So we say that the square root has two different inverses, the squaring function has two different inverses, positive square root and negative square root, whereas this function only has one inverse. And if I had plotted the negative part, then it would still only have one inverse if it was just the negative part. Okay, so the point is what you're declaring your domain and your codomain to be matters a lot, because it changes exactly what's going on. It changes the properties of the function. Now, why is this important? Okay, you got by in Calc 1 just sailing along using the formula to compute derivatives. But in Calc 3, the domain and the codomain and which are which matter, in the sense of you will have operations that will work when your domain is of one type and your codomain is of another type. And you need to be able to keep in your mind organized which techniques work for which kinds of functions. So let me explain an example. So, simple question. Calc 1 student can do this, a college algebra student can do this. Is this picture the graph of a function? Now think about it. I mean, take 5 seconds and just think about it. Think about why it is or is not. So you probably say no, it's not a function. And the reason why is it fails the vertical line test. Now, what's the vertical line test? The vertical line test is this idea that the rule of assignment of a function really is supposed to only assign one thing in the domain to one thing in the codomain. So when you're thinking of this as a function, you're saying, okay, my domain is the x-axis and my codomain is the y-axis, and I'm looking at this and I'm saying, well, where is this point going? Well, based on the fact that this is shaded in, it tells me that this x value has two different y values that are shaded above and below it. And that's not okay, because the rule of assignment should only assign one value to exactly one value. Nothing should go two different places for it to be a function. But with our expanded idea of what a function, what it means to be a function, you can say, yes, this is a function. And the difference is because we, instead of thinking of this as a function whose domain is the real line and whose codomain is the real line, turn sideways just so we can see it better, instead of thinking of a function in that, with that paradigm, we're going to think of this function as one whose domain is, well, there's a few choices, but we'll definitely pick its codomain to be R2. So the codomain is going to be points in the plane, and the domain, sort of the naive approach is to pick the domain to be the unit circle itself. You could do this. There's no trouble in doing this. And so we can define a function whose domain is a unit circle, so the things I'm going to plug into it are points, and really only the points on this unit circle. So, I'm kind of restricting myself to a certain subset of the plane for my domain, just as I did earlier with the real line. And the codomain I'll take to be R2. I could even choose it to be the unit circle if I wanted, but I didn't in this case. And I'm just going to be lazy, and I set it up so that I could choose the action of the function g, the rule of assignment, to be the what we call the identity map. That is, whatever you feed to this thing, it spits right back out at you. It's like y equals x. Like, in R, in the plane, the equation y equals x is this nice linear function. But this is the function, that takes an ordered pair x comma y, and it spits out the ordered pair x comma y. If we wanted to plot this function, we would get that picture at the top, but this is a legit function, although it's kind of silly. Okay, I mean, usually you would plot the function to learn something about the circle itself, as opposed to just kind of declaring it to be your domain, which is allowed. This is mathematics, but we can't. We won't use this in particular. What instead is more useful is to think of a function whose domain is a subset of the real line, so a one-dimensional domain, and whose codomains are R2. Now, you probably studied trigonometry at one point in your life, and when you did, you studied the unit circle. And what was the unit circle? Well, it was this thing that you looked at the angle that you wanted to compute the sine and cosine of, and then you looked at the coordinates of the point right there, and those coordinates said the x-coordinate was cosine, the y-coordinate was the sine, and I can find things on the unit circle like this. So, the general picture of the unit circle is that you have this input, this angle. I call it t, that your trig class probably called it theta, and we're going to want to define the function f to be the function that when I plug t into it gives me cosine and sine, and I can do that. Okay, we understand sine and cosine. You dealt with them through Calc 1 and Calc 2. So I can compute things. I can compute f of 0. Now f of 0 means put 0 into cosine, put 0 into sine. So cosine of 0 is 1, sine of 0 is 0, so f of 0 is 1 comma 0. So I'm associating to a one-dimensional function, function input, a two-dimensional function output. Same thing at, say, 3 pi over 4. So remember, pi over 4 is a quarter of a half of a quarter rotation, so an eighth of a rotation around the circle. So right here-ish would be pi over 4. 2 pi over 4 is pi over 2, which is the North Pole. And 3 pi over 4 is over here, halfway between the North Pole and angle pi over here. Now 3 pi over 4, if I take the cosine, I get negative root 2 over 2, and if I take the sine, I get root 2 over 2. And so, again, I'm associating to this number in the domain, this point in the codomain, negative root 2, comma, root 2 over 2. So this is a very nice function, and it shows you exactly why in this previous slide that we can understand this as the graph of a function. We just can't understand it as the graph of a function whose domain is R, just the real line, and whose codomain is also just the real line. We can instead understand it as a function whose domain is the real line, but whose codomain is R2, or in this other naive sense on the previous slide. So the textbook calls this sort of function the parametric equation with the parameter t. And so why do they write it like this? Well, they write x equals and y equals because in this function up here, we have the x coordinate of f is cosine, and the y coordinate of f is sine. And those are called parametric equations, and we call the variable t the parameter. Okay, so what can you do with this kind of thing? Well, you may have seen parametric equations before, so you may have plotted them before, but let's plot a few. So this is, I claim it's a spiral. Now, how do I know that, other than plotting it? Well, cosine and sine appearing in the x and y coordinates, like this, indicate circular motion. So I know there's some kind of circular motion going on here, but this t is growing. And so I know that sine and cosine are between -1 and 1, so if I multiply by a t over 5, that changes the amplitude of this cosine and sine as t gets bigger. So the amplitude of these are getting bigger, meaning that they're gonna spiral outwards in a very nice uniform fashion. So let's plot this, and again we can go to Desmos and we can type it in. Now when you're doing this and you're down here, hit the right arrow key, because if you don't, it's going to put stuff down here and you don't want that. So hit the right arrow key. Desmos is kind of finicky. See, it's kind of finicky, but you get used to it. If I did, you will. And what values are our t going between? Well, t is the independent variable of this function, and its domain is this. So this is the values that our t is taking from 0 to 2 pi. So if we type 2 times pi into this, then we get a nice little spiral. And it's corresponding to one full rotation because of the sine and cosine. Oh, that's great. Now, if we went a little further and did another rotation, that would take us to 4 pi. Or if we went 6 or 8 or whatever we could. And this is all very nice. I mean, it seems like they're all sort of equally spaced apart and all of this. If I can change that, of course. If I put a square on the t here, then that would make the y kind of take more importance. And so I should get some kind of oblong spiral. Oh, wow. There you go. So you can play with this all day. But what are some other interesting ones? That's my cat. It's kind of late and he's a little upset. Okay. Cycloids. So cycloids take this shape. And what is a cycloid? A cycloid is a graph you would get if you put, say, a circle here, and you made the point at the origin special, and you rolled this circle, and at some point it comes back down, and then that point rolls back up once it gets around the bottom. And so you end up with this kind of sideways going humps to the right. So there's an a here, meaning it can take any parameter value, like I'll put 3 there or something, and we'll see what we get. So let's try this one. So x is 3 t minus sine t, and the y has the same number, so 3, 1 minus cosine t. Yes. And our, we don't have values to go between. I guess I didn't for the spiral either, but 0 to 2 pi is pretty common. So if I do that, I get one hump of this cycloid. Now if I go a little further, I'll get 2, 3, a bunch, and it just goes. Now if I stop at just 1 pi, I get halfway, but the domain tells me exactly how far and much of the curve I want. So clearly defining your domain is very important in Calc 3, because we'll do things like take this to mean a wire, and we'll have to use magnetic fields or something and understand how the electric current is generated. Questions like this we can model with this kind of thing. And we can do even weirder things. Let me minimize my browser so I don't Alt-Tab between these. It'll be annoying to type otherwise. Desmos seems to be upset when you Alt-Tab to it too much. Okay, so let's choose A equal 3 and B equal, 2. You know what? Desmos is interesting. You don't have to pick the A and the B. I'll show you why. Let's just type it as is. A times B times cosine T minus B times cosine A over B plus 1 T. And we just add sliders. Now, we want a parametric thing. So that's the X. And now we have want to put in the Y. So sine T minus B times sine of A over B plus 1 T. And we need our T's. We don't want that. There we go. I shouldn't have added a slider for T. Let's take our T's from 0 to 2 pi. Oh, here we go. Here we get a cardioid. Now, if we slide this B around, we're picking different values, and we don't need that anymore. We'll see that some weird things can happen when you play with these parameters. What's going on there? Let's change the A. So we get some like clover looking things. We'll get some anti-clover looking things. If we take the B, swing it around, you get all kinds of interesting shapes. And we will look into a lot of these kind of things just for computational purposes. We can find tangent lines to these things, as you'll see soon, and that's great. So those were called epicycloids, and I don't know geometrically how they're defined, but those are their equations. Now, we're not super concerned with where the equations come from most of the time, but anyone who's interested, certainly you can come to my office or something and we can figure it out. I'm sure there's a lot of interesting geometry here, but for our purposes in Calc 3, just knowing an equation looks a certain way is more than enough. So one thing you'll be asked to do in the homework is to do what's called eliminating the parameter. Now remember, earlier we called T the parameter. And so when I have this parametric equation, sometimes I want to go back to an equation with just y and x, and you can do that. In fact, you can go from an equation in y and x to a parametric equation, which is the more common direction. But these are good problems just to get some practice and familiarity with these objects. So all you do is, I'll call. So this is from the book. I call this thing equation 1, and I call this thing equation 2. So I'll take equation 1, I'll solve for t. And how do I do that? I add 3, I divide by 2, okay? And then I just take this value of t and I plug it into equation 2, into this. And so I'll get 3 minus sine of that. And that's it. So this parametric equation is just a fancy way to write this guy, which, if you remember your trigonometry, is going to be a sine with an altered period, so it won't have one rotation in 2 pi, but in some different amount. And it will have a horizontal shift to the left because of the plus sign, and then it'll be flipped vertically, and then 3 will be added to it to shift it up. Now, is that apparent from this formula? Yes. If you remember your trig, is that apparent from this formula? Maybe a little less so. Maybe a little less so. So, certain forms of things are useful for certain questions. And for the topics in Calc 3, parametric form will end up being more useful, but of course, it sometimes, but not always, can be turned into something from a Calc 1 sort of perspective. But anything from the Calc 1 perspective can be parametrized. I guarantee you that. So that's it for section 1.1. In the next section, we'll actually do some calculus with these. So we'll find tangent lines and use them to find areas and things like that.